These are the answers to the Chapter 13 and 14 practice quiz. Starting with the multiple choice questions. Number 1. Based on Coulomb's law and the information in the table above, which of the following cations is most likely to have the strongest interaction with an adjacent water molecule in aqueous solution? Now, we've seen Coulomb's law problems before. Sometimes it talks about the attraction between two different ions in terms of the lattice energy. But this question is about solutions. So it's the attraction between a cation and a polar water molecule. We're looking for the strongest interaction, so therefore we should choose the ion that has the largest charge magnitude. So the answer is either magnesium or calcium with a +2 charge. And we want a small ionic radius since the attraction is inversely related to the distance between the charged particles. The best choice would be magnesium 2+. Number 2 is asking us to choose the molecule that is least soluble in water. Let's take a look on page 521 in the textbook, and we're looking at a picture of hexane and water. And it says that hexane is immiscible with water. The attraction between the polar water molecules and non-polar hydrocarbon molecules is not sufficiently strong to allow the formation of a solution. So in general, non-polar liquids tend to be insoluble or immiscible with polar liquids. So which of the 4 compounds that we see here in number 2 is non-polar? It's going to be the carbon tetrachloride because all of the dipoles are symmetrically arranged and cancel out. The molecules in choices A, C, and D are all polar. Number 3, one reason that could explain why silver chloride, AgCl, is insoluble in water. Remember that, and this is from page 515, that there are 3 types of intermolecular or interparticle interactions that are involved when a solution is formed. First, you have to break up the attractions between the solute particles. Then you have to break up or separate some of the attractive forces in the solvent. And then finally, you have to form attractions between solute and solvent. So in this situation, if we have London dispersion forces that are relatively weak, well, that's not talking about hydrogen bonding, but even so, that would not explain why silver chloride is insoluble. If it's easy to separate the solvent, then that would encourage the solution formation. So it's not A. In terms of ion-dipole forces, if they are very strong, that would favor the formation of a solution between silver chloride and water. But we're trying to come up with an explanation for why it does not dissolve. And then in letter D, even if the covalent bonds within a water molecule are very strong, the bonds that are covalent within a water molecule are not being broken in the solution formation process. So the correct answer is C. If it's difficult to separate the ionic bonds between silver and chloride, that would explain why it doesn't tend to break up and dissolve and dissociate in water. So correct answer is C. Number 4, we are looking at the formula of a hydrocarbon called toluene, C7H8. We know that it does dissolve in water, but only a little bit, so a very low solubility. We're trying to describe the intermolecular forces between water and toluene. The problem with choice A is if there are no attractive forces between toluene and water, that wouldn't explain why it does dissolve in water a little bit. So there has to be some level of attractive forces, although we're looking for rather weak attractive forces. Part B, number 2, or the second choice there, is not true because there's no hydrogen bonding whatsoever between a non-polar hydrocarbon and a polar water molecule. The hydrogen for hydrogen bonding would have to be directly bonded to either a nitrogen, oxygen, or fluorine, which doesn't exist in this molecule. And then in terms of choice C, Ion-dipole forces are between an ion, an actual charged ion, and a polar substance. So there are no charges. These are neutral molecules. There are weak London dispersion forces between toluene and water, so that's why it does dissolve, but only a little bit. Correct answer is D. For this next question, number 5, we have a diagram in which the solute is broken up. That's an endothermic process. The solvent has some separation. That would be also an endothermic process. So breaking attractive forces is endothermic. And then finally, forming attractive forces between solute and solvent, that's an exothermic process. So the correct answer to number 5 is C. In number 6, we have 4 substances, and we have to choose the one that has the greatest solubility in water. We've already talked about the fact that nonpolar substances do not mix with water very much. So we could eliminate choices C and D since those are both nonpolar. The difference between choices A and B, which both contain a polar OH group and could potentially form hydrogen bonds with water, is that one of these molecules is much longer than the other. There's a lot more carbons in the molecule in choice B than choice A. If you look on page 521, here is a chart that lists the solubilities of some alcohols in water, also in hexane. But focusing on the water, notice how methanol, ethanol, propanol are all completely miscible with water. But as we get longer, in terms of this carbon chain, the nonpolar portion of that molecule dominates its behavior. So hexanol is extremely insoluble in water because those 6 carbons make that particular molecule behave more like hexane than an alcohol with an OH group. So because the nonpolar portion of the molecule ends up making it immiscible with water, the best choice for number 6 is A, which happens to be called ethanol. Number 7, when most gases dissolve in water, the process is normally exothermic. Which of the following statements best supports this fact? Remember that the 3 types of attractions that are involved in solution formation is the endothermic, separation between solute particles, the endothermic separation between solvent particles, and the exothermic attractions between solute and solvent. So we're focusing on the exothermic portion. Let's go ahead and look at each of these 4 choices and see if they make sense. Letter A, the solubility of gases in water tends to increase as the temperature is increased. Well, first of all, is this true? And then does this support the idea of an exothermic process? No, this is not true. The solubility of gases actually tends to increase as you lower the temperature. And you can see this in figure 13.19. So gases are not going to become more soluble at higher temperatures. They become less soluble at higher temperatures. So A is not true. B, it's talking about energy released, which is exothermic, but it says when solvent-solvent interactions are broken. That's an endothermic process. So that's not true. And then letter D says most gases form strong covalent bonds. No, they would form some kind of either London dispersion forces or possibly dipole-dipole interactions, but the gases themselves are not going to form covalent bonds, and they're not going to react with water in that way. So the reason why C is true is that if it doesn't require very much energy to separate the gas particles from one another, then you are emphasizing the exothermic formation of the solution. So correct answer is C. Number 8, which of the following conditions would maximize the solubility of O2 in water? We've already talked about the fact that in terms of temperature, they become more soluble. Gases become more soluble at lower temperatures. So the correct answer is either A or B. What about pressure? Well, here you see in figure 13.15 that gases become more soluble as the partial pressure above the gas is increased. So we're looking for a higher pressure and a lower temperature to maximize the solubility of a gas in water. So correct answer is B. Number 9 is talking about rate of reaction. If you decrease the temperature, that's going to make the reaction slower in general. If you increase the volume of the reaction vessel using a piston, that's not really specific in terms of reaction rates. We haven't talked about that in chapter 14. And again, removing some hydrogen, that has more to do with a shift in the equilibrium. We haven't talked about that either. So the most obvious way to make a reaction go faster is to add a catalyst. Number 10, we have 4 different experiments. Which one of them is the slowest and which one of them is the fastest? So we can put them in order of increasing reaction rate. The slowest experiment should be trial 2 because it is involving the lowest concentration of HCl. The fastest experiment would be trial 3 because it involves the highest temperature. Now comparing trial 4 and trial 1, the only difference is that one uses powdered zinc and the other uses a zinc metal strip. So trial 1 should be faster than trial 4 because powdered zinc has greater surface area. So in order from slowest to fastest should be 2, 4, 1, 3. Number 11, approximately how long did it take for 75% of this particular violet compound, this is actually crystal violet, to react? Well, if 75% of this is reacting, then that must mean that 25% of it remains. If the absorbance was 0.62 at time 0, then half of that would remain at absorbance of 0.31, and when we cut that in half again, we get 0.15. So at 300 seconds, we have only 25% of the material remaining. In number 12, this has the potential to be a confusing question because we have lots of information. We could figure out the order with respect to X and Y and try to determine the rate law. But think about what they're really asking here. In trial 2, which of the reactants would be consumed more rapidly and why? On page 562, they're talking about coefficients in the balanced equation. So it says, consider the reaction where 2 molecules of HI decompose to give 1 molecule of H2 and 1 molecule of I2. Now, the rate of disappearance of HI would be twice as much as the rate of appearance of either H2 or I2. This is just based on the stoichiometry and the molar relationships. So we're looking at the fact that in the balanced equation, 1 mole of X is consumed, but 2 moles of Y are consumed. So therefore, the amount of Y should disappear twice as fast as the amount of X. So correct answer is D, just based on stoichiometry and mole ratios. Number 13, we have some information about how the concentration of hydrogen peroxide is decreasing over time, but this is a non-calculator question, so we can't take the natural log or do these types of mathematical operations without a calculator. On page 566, you can see an example of a reaction that has a coefficient of 2 for the N2O5 in the balanced equation, and yet the rate law says it's first order. Since the rate law must be determined experimentally, we cannot assume anything about the order by just looking at the balanced equation. On pages 569 to 571, they show you examples of first order and second order kinetics. One way to distinguish between first and second order rate laws is to graph both natural log of the concentration and 1 over the concentration against time. And if the natural log plot is linear, it's first order. And if the 1 over concentration plot is linear, it's second order. So here, the best choice would be C. The reaction is first order if the plot of natural log of concentration versus time is a straight line. Number 14, we're looking at activation energy here. So on page 577, we see a diagram and they show you activation energy. It says the rate depends on the magnitude of the activation energy Generally, the lower the value of activation energy, the faster the reaction. Or you could say the converse of that statement, the higher the value of activation energy, the slower the reaction. So comparing the activation energy for A and B, A should be slower and B should be faster. So correct answer, reaction A is slower than reaction B because it has a higher activation energy. So for number 15, we have some data. They've already done the math for us. This is not concentration versus time, but since we're talking about gases, the pressure is monitored over time. And that's still fine in terms of comparing the disappearance of N2O5 over time. We have pressure values, but we can still treat this as if it were concentration. Which of the following correctly describes the reaction? Let's see how long it takes to go from 100 atmospheres to 75 atmospheres. Well, it takes 100 minutes. That's the half-life. And the half-life is constant. It takes 100 minutes to reduce the pressure by half. Since the half-life remains constant over time, the reaction is first order. And you can see this on page 573. They've talked about first order kinetics. We have a graph, and we're seeing an example of that. It says we see that the half-life for a first order rate law does not depend on the initial concentration of any reactant. In a first order reaction, the concentration of the reactant decreases by 1/2 in each of a series of regularly spaced time intervals. So that's one way of proving it's first order. Another way you could prove that it's first order is to focus on the natural log part of this table. It takes 100 minutes to go from 5 to 4.3. That's a difference of 0.7. And then another difference of 0.7 and 0.7. So every 100 minutes, the value of natural log of pressure decreases by 0.7. So the plot of natural log of pressure versus time is going to be a straight line. So we're definitely convinced that it's a first order reaction. Now for number 16, they want to know what the rate constant is. We've got to focus on the number as well as the units. On pages 570 to 571, it shows you the example of the first order rate law, the integrated rate law, and then says, for a first order reaction, the graph of natural log of concentration versus time gives a straight line, and the slope is negative k. So what's our slope in this situation? Well, remember that the natural log of pressure was decreasing by 0.7 every 100 minutes. So the slope of that line would equal 0.7 over 100. And that would equal negative k. So therefore, that's 0.007 for the number, and the unit would be inverse minutes. Since natural log has no units, you're dividing nothing by minutes. You get inverse minutes. So we have 1 over time, and we have 0.007. So correct answer for 16 is A. For number 17, we're talking about mechanisms. If the first step is slow and the second step is fast, we should be focusing on the slow step. How can we get an overall rate law that's first order with respect to NO2 and first order with respect to F2? Remember that the slow step, this is on page 585, the slow step, the rate determining step, will control the rate law for the overall reaction. And in the give it some thought question, well, why can't the rate law be deduced from the balanced equation for the reaction? And the answer to that question, which is in your book, is that most reactions do occur in elementary steps, and the rate law is coming from the elementary step, that's the slow step, not by the overall balanced chemical equation. So we're not focusing on anything except the slow step. On pages 585 and 586, they show you an example where the first step in the mechanism is slow and the second step is fast. Now we have 2 molecules of NO2 reacting in that slow step. Because step 1 is slow and step 2 is fast, step 1 is the rate determining step, and because 2 molecules of NO2 are involved, it's bimolecular and would be second order. Had you only focused on the overall reaction, there's only 1 molecule of NO2 in the balanced equation overall. That wouldn't have told you that it's second order with respect to NO2. Let's focus on the slow step. So here, if the rate law is first order with respect to NO2 and first order with respect to F2, there should be one molecule of NO2 and one molecule of F2 in the slow rate determining step. So therefore, choice B, which has exactly those requirements, is the correct answer. Number 18 is also talking about mechanisms. Now the rate law is first order with respect to X2, so therefore in the slow rate determining step, there should be exactly one molecule of X2. So no matter what happens after the slow step, both of these mechanisms are consistent with it being first order with respect to X2, since there's exactly one molecule of X2 in the slow step. So correct answer here is that both mechanism 1 and 2 are consistent with the rate law. Number 19. We've got 4 statements. Which of the following statements is true? In this mechanism, the first step is actually fast, reversible, and the second step is slow. On page 587, here's an example, just like that, where you have a fast equilibrium followed by a slow step. And it mentions that because we're focusing on the slow step, that the rate would equal K times the concentration of NOBr2 times the concentration of NO. Again, first order because there's only one molecule of each chemical. Well, here's the problem. NOBr2 is not a reactant or a product, it's an intermediate. Intermediates are usually unstable and have a low unknown concentration, so therefore you cannot write a rate law that depends on the unknown concentration of an intermediate. This is not desirable. We want to express the rate law in terms of the reactants. So focusing on how we can get rid of this NOBr2 in the rate law, we did this in our chapter 14 packet. We take a look at that first fast equilibrium. We write that the rate of the forward reaction equals the rate of the reverse reaction. We substitute for the NOBr2, and when we're all done, we've now replaced the NOBr2 with one molecule of NO and one molecule of Br2. So in the final rate law, it's second order with respect to NO and first order with respect to Br2. We have to do a similar thing with this problem. Focusing on the slow step, which is first order with respect to this intermediate N2O2, and first order with respect to oxygen, let's get rid of the N2O2. Let's write the fast equilibrium, so rate of the forward reaction equal to the rate of the reverse. We're going to rearrange the equation, solving for N2O2 and then substituting for that. Our new rate law is now going to be second order with respect to NO, because it came from that first step, and first order with respect to oxygen. So it's looking like choice D is correct. Let's go ahead and talk about why A, B, and C are wrong. Step 1 involves 2 molecules of NO, so it's bimolecular, so it cannot be A. If you increase the concentration of the reactant, NO, it's definitely going to speed up the reaction. It's going to make it go faster. And if you raise the temperature, that normally makes the rate constant go up as well. We've talked about that. So correct answer for 19 is D. Number 20. Just because molecules collide doesn't necessarily mean that they're going to produce products. The observed reaction rate is only a small fraction of the calculated collision rate. So why is that? On page 576, more is required for a reaction to occur than just a collision. In most reactions, the molecules must be oriented in a certain way during a collision for a reaction to occur, so they can sort of line up and form their new bonds. So correct answer for number 20, the 2 reactant particles must collide with a particular orientation in order to react. All right, 21, we see a catalyst, and that would be consistent with lowering the activation energy. The most dramatic catalytic effects come from lowering the activation energy. As a general rule, a catalyst lowers the activation energy for a reaction. This is on page 590. A higher temperature in path 1, no. A higher temperature in path 2, no. Looking for a catalyst, and the catalyst would be in path 2. All right, well, now we finished the multiple choice questions. On to the free response questions. Number 1, the structures of pyridine and benzene are shown above. Here on page 515, you can see a variety of intermolecular or interparticle forces. We have London dispersion forces between typically all molecules, but especially if they're nonpolar, that's all they have. Dipole-dipole forces between polar molecules. Hydrogen bonding, when you have a hydrogen directly attached to either an oxygen, nitrogen, or fluorine. And ion-dipole forces. What do we have going on with pyridine and water? Well, pyridine is polar because of that electronegative nitrogen atom. It's not just an ordinary hydrocarbon. And then benzene is an ordinary hydrocarbon, so it's nonpolar. So pyridine is going to have both London forces and dipole-dipole forces, but no hydrogen bonding. Benzene is only going to have London dispersion forces with respect to how it forms attractions with water. So which of these substances should be more soluble in water? Hopefully you can see that the example we did earlier from the multiple choice, where polar substances do not really mix very well with non-polar substances, that's consistent here. The benzene is non-polar, so it's only going to dissolve a little bit in water. But pyridine, which is polar, is going to dissolve a little bit more. And of course, you cannot say something in part C like dissolves like. You've got to be specific and talk about the attractive forces and who has a greater strength. So the dipole-dipole forces between pyridine and water are stronger than the London dispersion forces between benzene and water. And since the attractions between pyridine and water are more favorable than the attractions between benzene and water, you would expect pyridine to be more soluble in water than benzene is. Before we draw the attractive force between pyridine and water, let's focus on the location of the dipole. The nitrogen atom in pyridine is the most electronegative atom in this molecule, so it would carry a partial negative charge. Now the CH bonds, the hydrocarbon bonds, are generally nonpolar. So we're focusing our attention on the nitrogen having a partial negative charge. Of course, with water, we have both a partial negative and a positive charge. So how can we get the pyridine to be attracted in a specific way to the water molecule? Well, if we take the negative portion of pyridine and we attract it to the positive portion of water, then this would be the best attraction you could draw. I would not accept an attraction between the hydrogen of pyridine and the oxygen of water, since that hydrogen of pyridine is not really considered a strong polar bond. That CH bond is generally nonpolar. So this would be the best attraction between the negative and positive charges. All right, on to number 2. We have a 3-step mechanism in which the first step is slow. We're going to go ahead and add these 3 steps together to write the overall balanced equation. So crossing off the chemicals that appear on both sides gives us an overall balanced equation of 2 molecules of hydrogen peroxide decompose to give 2 molecules of water and 1 molecule of O2. The substances that are intermediates are the ones that we crossed off. So both of the HO and the HOO radicals with the little dots there, those are the intermediates that appear on both sides. The rate law is focusing on the slow step, the rate determining step, which has only 1 molecule of H2O2. So the rate law should be first order with respect to hydrogen peroxide. Here we have a graph in which the concentration of hydrogen peroxide is disappearing over time. It takes 0.5 hours to go from 2 molar to 1 molar. It takes 0.5 hours to go from 1 to 0.5. So again, you can see the half-life is constant over time. And we talked about that earlier. Once the half-life is constant over time, we know it's going to be first order. Now, to justify your answer, you could either say what I just said, which is the half-life is constant and does not change over time. Another way you could justify that it's first order would have to do with the natural log. If you took the time to calculate the natural log of concentration over time, you would see that the natural log is decreasing by exactly 0.693 every 0.5 hours. So you would get a straight line if you plotted natural log of concentration versus time. That could be another way to justify why it is first order. So because we know that the rate law was first order, and we just got that information from the experimental data, yes, the order of the reaction was consistent with that rate law, which was written from the mechanism. So now we're going to calculate the value of K. If the half-life is known, then we can rearrange the equation and just solve for the value of K. 0.693 divided by the half-life, which in this case is 0.5 hours. We have units of inverse hours, and we have a value of 1.39. So K equals 1.39 hours to the negative 1. The last part, part G, we have 4 different scenarios. We have to consider, is that particular value going to be higher, lower, or the same for the catalyzed reaction comparing it to the uncatalyzed reaction? And we have to justify our answer. So here we are looking at the delta H. Now look at this graph. Is the delta H changing for the catalyzed or the uncatalyzed reaction? No, the delta H is the difference between the energy of reactants and products. So the value of delta H in the catalyzed reaction is the same as the value of delta H in the uncatalyzed reaction. So what's our reason why? Because a catalyst only affects the energy of the pathway, the activation energy. It does not change the potential energy of either reactants or products. Well, what about the activation energy? Of course, that's going to be lower. A catalyst provides a lower energy pathway. So the value of activation energy in the catalyzed reaction is going to be lower than the value of activation energy in the uncatalyzed reaction. That's what a catalyst does. Provides a lower energy pathway. The half-life, well, if your chemical reaction is going faster, then that means the half-life is going to be less. It's going to take less time, even though it's a faster rate. The time involved is going to be smaller. Because a catalyst speeds up the reaction rate, it's going to require less time for the concentration of a reactant to reach half of its original value. And then part 4 of this question, part G, the rate constant. At a faster reaction rate, K will increase. So a catalyst speeds up the reaction rate, and if the rate increases, and we're assuming that the concentration of hydrogen peroxide, the initial concentration remains constant, well, something else has to increase. So if the rate goes up, then the value of K would increase as well. Another way you could have justified your answer is to use that equation showing that K is inversely proportional to the half-life. We've already said that adding a catalyst causes the half-life to decrease, so therefore the value of K must increase. All right, well, these represent the answers and explanations for the Chapter 13 and 14 practice quiz. I hope that was helpful. Thanks for watching.